Hi, today I am presenting my paper on a federated multigraph integration approach for connectional brain template learning. This work has been done at Basura Lab by myself and supervised by Dr. Islam Rekik. Nowadays, accessing large-scale datasets is much easier. However, it is challenging to collect all these clinical datasets in one place because of the data sensitivity and privacy. Thus, it's hard to design an algorithm for integrating connectional brain templates, CBT for short, since such algorithm needs brain connectomic datasets, which are clinical. So the question arises, how can we design an algorithm for integrating CBTs using clinical datasets located in different places? There are many studies on integrating CBTs in the literature. For instance, one proposed clustering-based multi-view network fusion by the similarity metrics of their connectivity patterns. However, its success depends on the number of clusters during fusion step. The other offered to form a tensor that contains common cross-view features and then fuses distinct layers of this tensor into a CBT in a nonlinear manner. Nonetheless, this algorithm just captures linear patterns, and its training procedure is not in an end-to-end manner. Another one proposed an algorithm called Deep Graph Normalizer, DGN for short, which is the first geometric neural network, GNN for short, to learn CBT from a given multigraph population, even though its loss function does not evaluate the topological soundness of generated CBT. MGNNet offered a GNN model to learn CBT with a loss function preserving topological soundness of generated CBT, but it can take advantage of private datasets in different hospitals. We chose the DGN algorithm to generate CBT from a multigraph population. We used it in every hospital's computer. We then designed a federated pipeline so that we can train these DGNs separately and then transfer trained models' weights to a central server so that we can obtain the information from clinical datasets without sharing them. Next, we'll see how federated learning works. First, a DGN model is initialized in the server and its weights are shared with hospitals. Hospitals that are not trained in the current round do not update their weights, shown in red, whereas those that update are shown in green. Selected models are trained. After that, they just pass back their weights to the server. Received weights are averaged in the server, and information from different datasets are combined in this way. Let's have a deeper look what happens in a selected computer for a specific round. In each round, in selected computers, each hospital randomly samples a subset from its local datasets for training. These graph-defined data are transformed into tensors. Only one tensor is passed to the DGN model in every batch at the same time. Several tensor operations are applied to the output feature vector, and a CBT that represents the population of the dataset of a hospital is generated finally. Trained model weights are passed back to the central server. Following the collection of models' weights in the server, their weights are averaged with temporary weighted averaging, whose formula is given in the upcoming slide in a layer-wise manner. Thus, an updated version of the global model is generated. Next, weights of the updated global model are sent to hospitals. Given the generated CBT CJS for subject S of hospital J and a random sample subset S of training subject indices, SNL loss function is defined as follows. When models send back their weights to the server, we can denote hospital J's loss in round T as follows. Using the function above, we can express the federated loss function of all hospitals in round T as follows. We, on the other hand, formulate the federated model's weights in the following way. We notice that the more recently a hospital is selected to be trained, the stronger the contribution of its weights to the following round. Thus, we formulate this as follows. In our experiment, we use two different datasets, normal control and autism spectrum datasets, containing 186 and 155 subjects respectively. We evaluated our algorithm using threefold cross-validation and generated the CBT. We benchmarked DGN, DGN with federation, and DGN with federation using temporary weighted averaging strategies. We used Frobenius distance between generated CBT and validation sets of threefold cross-validation. We see that DGN with federation using temporary weighted averaging strategy outperformed the other two in 3 datasets, except normal control left hemisphere. DGN with federation in normal control left hemisphere dataset outperformed DGN strategy. In this work, we introduced the first federated framework for integrating connectional brain templates so as to take advantage clinical datasets in different computers. We showed that our framework and strategies outperform the DGN algorithm. In our future work, we'll design a federated integration strategy that handles not only the same number of the brain connectivity views, but also different ones. Feel free to check our recent review paper on GNNs in network neuroscience, covering recent GNN architectures for brain connectivity integration, classification, super resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira-lab.com. Thank you.